Nottingham, and he is a coordinate for our project for the project High Performance Computing in Wind Energy. Let's welcome Xuerui. Before you start, would you mind if you record your presentation for later publishing on the website of the project?
Oh yes, I'm happy.
Thank you very much.
My PowerPoint now.
Yeah, please do start, and I would like to ask everybody again. Please turn off your cameras and microphones till the end of the presentation. Thank you very much. Please go ahead, Xuerui.
Thanks, Mohsen, for the introduction. Thanks, everyone, for attending our event. So my talk is about a hybrid solution for wind resource assessment. It's basically to use limited onshore LiDAR or mast measurement to predict the offshore wind. So the main work is done by Bassam Al-Sharfi at the University of Nottingham. The measurement we used here in this work is from DTU, while the simulations are mainly run by the Wolf group, led by Dr. Jake Badger. So this project and all the work here, most of the work we presented in this workshop are funded by the H2020, the Future and Emerging Technologies Program with such an agreement. It is called High Performance Computing in Wind Energy. Okay, so I will firstly introduce the importance of wind resource assessment and the techniques available, and then discuss some algorithms for data fusion. It's a new technique for wind resource assessment. Then I will present a test case, which is around the coastal line of Denmark. Then after pre-processing the data, the measured and the numerical data, I will present the result of the data fusion, which is for the prediction of offshore wind indirectly. Okay, so here are some direct methods for wind resource assessment. The left one is a mast. So the mast result is regarded as accurate, but apparently this is quite expensive. In Europe, to establish an offshore mast would cost $50 million. Well, the second one is also a direct measurement. It's a floating LiDAR. Apparently, this one requires regular maintenance. Otherwise, it does not generate outcomes reliably. Well, the third one is by satellite SAR images. This is also pretty accurate. You can measure the wind 10 meters above the sea level. So apparently, in this case, you need another algorithm to project the wind to 50 meters or 100 meters above the sea surface so as to use it for wind resource assessment. And also, you need some other devices to measure the wind direction. So this is a requirement of this method. And apparently, you need a satellite also. Well, the first three are physical measurement. The last one is a mesoscale numerical simulation. While compared with the first three direct physical measurement, the last one is regarded as relatively with low fidelity. Well, it's just relatively. So here are the four main types of direct wind resource assessment for offshore wind. Then we have some indirect methods. The idea here is to combine two forms of input data. So here, one form of the input data is the onshore measurement. It can be from LiDAR, mast, MET station, and so forth. The data is usually sparse in time and in space. So for example, if you put a LiDAR at some position onshore, then you can only measure the wind at this location, right? And you can only put it there for a few months. And over this few months, the output may be also intermittent. It is not consistent. And secondly, we can have the onshore and offshore Wolf simulations or CFD simulations. Well, this data is relatively cheap, but it is abundant. We can have it continuous in time and in space. But this one, compared with the direct measurement, it is of low fidelity. So the indirect assessment is to combine these two data, one onshore accurate measurement, one offshore simulation result to obtain the offshore wind. This is an indirect measurement. So here we bypassed the direct offshore measurement. You don't need to establish a mast in the water or to put a LiDAR there. But we use the onshore measurement and project it numerically to the offshore region. So an immediate solution is called the speed up. Speed up is simply to get the ratio of the wind at an onshore location and offshore location, then combine it with the onshore measurement, you can obtain the offshore wind. This is a quite straightforward solution. It is cheap, but apparently inaccurate. While the most accurate, or one of the most accurate approach would be the adjoint method. So in this method, we can tune the parameters in the numerical solvers, such as WRF or CFD solvers, so that its outcome agrees with the measurement at the given time and space locations. Apparently, this method requires to change the code, and it is very expensive to compute. So here we propose something between them, between speed up and adjoint. We call it a multi-fidelity data fusion. It is a data assimilation technology. The accuracy will be based on, will be between them, while the cost is also between these two solutions. So basically, we want to propose something more accurate than speed up, but with almost the same cost. So here is the basic idea of the multi-fidelity fusion. So here we regard the that we have 2 points, an onshore point and an offshore point. Our goal is to project the onshore data to offshore. So in the onshore point, we have a continuous data, which is from the simulation with low fidelity. And we also have a sparse data, which is from measurement, but with high fidelity. Okay, so combine them, we can get the full expanded data at this onshore point. So this is because our sparse data, which means the LiDAR or mast measurement, does not span a long time. We may need 10 years of data, but the measurement may be only for several months or weeks, and it is also intermittent. So by this technology, the temporal fusion, we can obtain a continuous onshore data. Basically, this approach is to complete your onshore measurement based on the very limited available data. And then we combine this onshore data with the offshore numerical data to obtain this merged offshore wind. So you can say in this technology, we require 2 forms of data. One is continuous data from simulation with low fidelity. One is sparse, it's from measurement, but with high fidelity. So here the red points denotes the measurement. You see here, if you have 3 LiDARs at 3 locations, it may generate output at some time positions. Well, it is not continuous, apparently. Well, in location, if you only have it installed at 3 locations, apparently at other locations, you don't have output. But for the WRF data, for the simulation data, it is consistent. It is everywhere across this domain. It is continuous in time and space. So taking into account the feature of these 2 forms of data, we want to find an algorithm to combine these 2 sets of data. And the final aim is to predict the offshore wind from the onshore measurement. Okay, so this is algorithm. I try to elaborate on the result rather than the algorithm. So here I just outlined the main ideas. So we have 2 main steps. One is to regard the high fidelity data as a function of time and the low fidelity data. So here the high fidelity one is the measurement, is your LiDAR result, and the low fidelity one is the WRF result. Again, when I say low fidelity, it is only relative to the direct measurement. Okay, then we regard this function as a Gaussian process, and from the Gaussian process regression, we can estimate the overall distribution of the high fidelity data. And another step is to further consider the high fidelity data as a function of time, the low fidelity data, and the first, second, third order differentiation of the low fidelity data. So this is because our low fidelity data is from WRF simulation. It is available everywhere. It is time continuous, so it is differentiable. And then we take the differentiation of them to represent the curvature of your curve. And therefore, by considering those differentiations, we can add more information in this prediction, in this model. Okay, so the second step is the spatial fusion. This is relatively straightforward. We just use a nonlinear auto regression with external input. So we have the input and the history of the point we are estimating and to generate the present output. So basically here we have two steps to reach this data fusion. One is a temporal fusion, one is a spatial fusion. The temporal fusion is to complete your LiDAR measurement. If you only have a few months of LiDAR, we want to expand it to 1 year or several years. And then it's the spatial fusion. We want to project the wind from onshore to offshore. So here is the test case in the west of Denmark. So overall in this region, our DTU partners have run LiDAR measurement and WRF simulations. So here we have LiDAR measurement at both onshore and offshore so that we can use the offshore measurement to validate this method. Okay, so basically we will use the WRF method, WRF data to establish the model and then use the LiDAR data as the input to estimate the offshore wind. So before we apply those methods, we have to run some data filter to remove the localized noise. So here we can't run a Fourier decomposition. It's just because the noise in the wind signal is actually localized. So many of them may be just localized in space and in time. So here we need some other technology called empirical wavelet transform to smooth the wind speed time series, just to ensure our data sequence is differentiable. Because as you noted before, we need the differentiation of the WRF data. So here we have to remove the high frequency noise. And after the pre-processing, after the filtering, we designed 3 approaches for the temporal fusion. So again, the purpose of this is to fill our inconsistent or incontinuous LiDAR data. So here you can see that in all these 3 pictures, we denoted the LiDAR measurement by the points, by the dots. You can see that those dots are inconsistent. So at some positions, you have very dense measurement and outputs, which means the LiDAR is working pretty well, while at some other locations, maybe the machine malfunctions, so you have no output at all. And here, if we combine it with WRF, we can obtain an hybrid solution spanning a longer time. So here we didn't actually plot the longer time. We have designed 3 methods. The first one is to just combine WRF and LiDAR, and the second is to add the first and the second order derivatives of the WRF data, and the third one we further consider 2 horizontal velocity components. In the first 2, we only consider 1 velocity component. That is the magnitude. So here you can see in the final picture, we showed the accuracy of the measurement of our prediction against the LiDAR measurement. So here we can say that a direct WRF returns the highest root mean square error, while after our data fusion with method 1, hybrid 1, we significantly reduced the error. Well, when we move from method 1 to method 3, the error is reduced to around 0.8 or 0.99 meter per second. Okay, then a further extension of this idea is to consider even more layers of fidelity. In the last page, I used the LiDAR and WRF data, and here we can consider LiDAR high resolution WRF and low resolution WRF, and they have highest fidelity medium fidelity and low fidelity, respectively. But this is to say that maybe some quick and dirty simulation results are also useful. So here we just try to explore as much as we can, exploit as much as we can from the simulation result, even if they are with low resolutions. So let's now consider this low resolution, or we add them into our algorithm. So now we consider 3 layers of fidelity. So now you can see that this result is actually even better than the first 3 methods, which only use 2 layers of fidelity. It indicates that some quick and dirty numerical simulation results is indeed helpful when we combine it properly with the measurement. And then we further consider 4 layers. It stops improving, which means there's a limit by considering more layers of fidelity data in this data fusion. For these 3 layers, we reach a root mean square around 0.6 meter per second. So for fluid mechanics, this can be regarded as the LiDAR data can be regarded as the wind tunnel measurements, and the high fidelity WRF can be regarded as direct numerical simulations or large edge simulation results, while the low resolution WRF can be considered as the runs result also. So the same method therefore can be applied to CFD problems and to combine results with different fidelities so as to reach a better solution, a more accurate solution. So here is the spatial fusion. The purpose here is to project our onshore measurement at such points, onshore points to the offshore point. And here is our brief result. And then we can combine the temporal and the spatial steps together. And here we can say that this is our overall result. Because this is a Gaussian process, so we can also predict the zone of sensitivity, zone of uncertainty. So overall, our root mean square error is less than 9%. So this is to say we only used the onshore measurement, but in light of the numerical results, we can make a good prediction of the offshore wind. Okay, as a summary, we have run an temporal data fusion so as to fill the intermittent LiDAR measurement and also expand it to a longer time domain. And we run a spatial and temporal data fusion so as to use onshore measurement, which can be from LiDAR, mast, or meta stations, and so forth, to estimate the offshore wind. In this way, we can bypass the direct offshore measurement. So for future works, we are doing more layers of fidelity. That is the one I just presented. We have 4 layers of data. Another one is the data fusion in the full 3-dimensional domain. What I presented here is just in the 2-dimensional domain. We have time and 1 spatial coordinate. Later, we can extend it to X, Y, Z, T, 4D domain. And also, we will test more cases, such as the Portugal site and the Santa Catarina site in Brazil, as Jake and Marta has just mentioned. So both of them are HPCWE test cases. Okay, so here are our contact information for the project HPCWE. Please note that all the videos and the PowerPoint of this workshop will be attached to our website. So we have a few social media tools. Please feel free to follow our updates. Then thanks for the support of the commission, and thanks for your attention. If you have any questions, I'm happy to take them.
Thank you very much, Xuerui. I would like to ask audience if anybody have any question, please go ahead, use the raise hand option, or just write your question, or just go ahead and unmute yourself and ask. So apparently there isn't any till now. Let me ask you one question myself. You mentioned you're using some filter for pre-processing of data to remove the noise. And how would affect the fidelity of the data?
I think Just a minute. Let me return to my PowerPoint. Okay, so we have shown that in this data pre-processing, it just changes the WRF data slightly. So because we regarded the WRF data as the low fidelity one, so a slight change of it would not change too much. So we regard the LiDAR data as the direct result. So we don't want to change the LiDAR data. Well, for the WRF, it's already the low fidelity one in this algorithm. So even if it is changed slightly, it does not matter. And our final result is based on the comparison with the LiDAR measurement, and therefore the distortion during this data filtering is already taken into account.
Okay, thank you very much. Thank you very much for your presentation. Let's move to the next presentation.
Thanks.
The next speaker is Clementine Liguanic. Let's welcome her and